Hi, this is Aaron for Aaron Does Science. This is going to be the first video on the channel. It's really just a test of the technology to see if I can use the screen capture software and the drawing software. Apologies for the quality of the video. Both my microphone is rubbish, the capture software is rubbish, and my tablet has decided to act up today. But moving on with the video is just going to be a simple introduction. It's going to be a separation of the Schrödinger wave equation into its to examine standing or steady states or standing states, and also to find the time independent Schrödinger wave equation. So there's a few things I've written out on my little virtual whiteboard thingy here to start with. The top is the Schrödinger wave equation. I'm sure anyone watching this is already familiar, but I'll just go through a few of the little bits. This h bar Planck's, so h minus h bar over 2m, the Laplacian of the wave function, which is this is the time dependent Schrödinger wave equation, so it's dependent on position and time, plus the potential potential energy operator acting on the wave function again, which is again a function of position and time, is equal to the imaginary number, h bar, times partial d partial dt of the wave function. I've also made, for this derivation, two assumptions have been made for splitting the wave function. The first is that the wave function, this capital psi, which is a function of position and time, can also be written as two functions, one a function of position only and one function of time only, and we've denoted those by phi, small phi, and chi, small or capital chi actually, respectively. The second assumption made in this derivation is that the potential energy operator operates only on position, so it will not. Now this will become important. This importance will become apparent in a few moments when we'll see that this means that it does nothing to this chi function here, the potential operator. Okay, so the first step of our derivation of the steady state and also of the time independent wave equation is to substitute for everywhere we have capital psi here, the wave function, to substitute in phi chi. So what we get if we do that, tablet acting up, is we get minus h bar, that should be an h bar squared. Yeah, minus h bar squared over 2m multiplied by chi by the Laplacian, so del squared of phi. Now where this is important, the reason chi is not affected by the Laplacian is because the Laplacian is the partial derivative of the wave function with respect to each of the three dimensions that we're using, or each of the dimensions we're using, whatever those may be, x, y, and z, r, phi, and theta, whatever coordinates in whatever coordinate system we're using. This means that if you do, so this is coming from the product rule of differentiation, and if you do that yourself, you can satisfy yourself that we can in fact write this, because what we'll get is, if we do the product differentiation, what would actually be would be phi Laplacian chi plus chi Laplacian phi. But what we find is that since this chi does not depend on time, does not depend on position rather, its Laplacian would be 0. So we're just left with the second term, this chi Laplacian phi. Actually, it would be a little more complicated than that because it's squared here, but at the end, sorry, I'm slightly wrong. It would be a little more complicated than that actually, just because of the squared. You'd be doing it you'd be doing the product rule twice, but at the end of doing that product rule, what you would end up with would be this. This would be the only term that would not include a position derivative of a function of time only, i.e., this is the only term that would not be 0, or not necessarily be 0. So we end up with that, plus chi, sorry, tablet acting up again, chi v phi. And again, you can to look at this one, again, it's by a similar principle. V is acting only on things that are a function of position, as we've said over here. Since chi is not a function of position, it is unaffected by the position of the potential operator, and so it doesn't matter what order we write it in. And it's just going to be useful for us later to write it out here. We could have written it over here, it really doesn't matter, but it's going to be useful for us to write it over here. And that is going to be equal to I h bar. I h bar doesn't change, it's just constant. And now again, by exactly the same token over here, of the product rule with a time function and a position function, we're going to be able to write, oh, for God's sake, that's wrong. If we're going to write IH bar phi partial d partial dt of chi. And again, we can do this over here because this is even easier than over here, because we only use the product rule once, and here what we actually are going to get is we're going to get chi partial d e phi plus phi partial d e partial dt chi. But since this does not depend on time, it's got that term, the term with this being derived with the response with respect to time will be 0. So this will be the only non-zero term in our product rule. So that is the first step. The next step is just to look at this and say, well, what do we want to do? Well, what we're going to do is we're going to divide everything by this, by the wave function, by phi chi. Again, why we're doing this will become apparent in a moment. That's my tablet acting up yet again. It's going to do that a lot, so apologize. It's one over phi Laplacian of phi plus 1 over phi v phi is going to be equal to IH bar plus 1, multiplied by 1 over, for God's sake, this stupid tablet, 1 over chi del t of chi. So this is our next step. And now what we're going to do is we're going to see something very interesting about this little structure here, and that is that the left hand side is a function only of position and the right hand side is a function only of time. and they're both being derived. Now, in order for this to happen, that this side is only a function of position and this side is only a function of time, but they are equal, would have to mean that they are both equal to some constant. Now, the reason we say they're equal to some constant, well, it's a little bit intricate, but what it ends up being is that's the only way that they're going to always be the same, since they both depend on two completely different things. Just a caveat, when I say completely different things, remember the Schrödinger wave equation is a non-relativistic equation. It deals with a classical notion of time and space being two separate things and time being an absolute quantity. It's not relativistic. The Dirac wave equation is relativistic, at least special relativistic. It's not general relativistic. There is no entirely successful or unification of general and special general relativity in quantum mechanics, though there are multiple attempts. The various things like string theory, brain theory, what else? Loop quantum gravity. Those are all attempts at unifying it. But anyway, what we'll see here, and it will suit our needs for now to say that that constant is h bar omega. Now, h bar omega, of course, is going to be the energy of the particle. Now, that finds justification in the theory itself that we're going to have energy. Why we already know it's going to have to be an energy. Why? Well, because these things all have units of energy. Although again, that's apparent because of this V. This is finding a potential energy, which means this thing must have units of energy. So we'll say, well, why not say that that energy is the total energy of the particle? Let's define total energy of the particle to be that. And total energy of the particle is also h bar omega from Planck's theory. So you can satisfy yourself of that. So now what we are going to do, give me one moment. Oh yes. Sorry. Now what we're going to say is that this lovely chap here, if it works, this is what we were trying to look for. This is the time-independent Schrödinger wave equation. This thing is going to be equal to h bar is going to be equal to this thing, h bar omega, the total energy of the particle. This is, if we skip out this little bit in the middle, is the time-dependent, or time-independent rather, Schrödinger wave equation.